me that there is a tradition of 10 minutes after the announced hour here.
Not for everything.
But I couldn't stand it because I'm too impatient to hear from our speaker this morning, who I'm very happy to introduce to you, Andras Guillen. Was a graduate student at CWI in Amsterdam, working with Ronald de Wolf, co-advised by Harry Berman, two of the giants in the field of quantum algorithms. And this morning he will give us an overview of all quantum algorithms, and he's currently a postdoc at the Institute of Quantum Information and Quantum Matter, or just Matter at Caltech.
Thank you for the very nice introduction. Is the mic on? Okay. So I'm really grateful for Ike's words today and also from yesterday. So I will talk about an overview of quantum algorithmic techniques. I really want to group together some main ideas about quantum algorithms and show some applications. And I try to cover most big ideas and big distinct tools in quantum algorithms in the first talk. And in the second talk, I will talk about quantum singular value transformation, which is really a summary of the very nice techniques that Ike, Guang Hao, Theodore Yoder, and many other people developed over the past decades. So first, I will talk about quantum algorithms, and this is just my kind of grouping the techniques. Some of the techniques are fairly simple, some are more elaborate. So I will start to talk about the quantum Fourier transform and related algorithms. Then just a quick intro to swap test. Then I will talk about the most fitting applications to quantum circuits when we think about representations as unitaries and then just use them as quantum circuits. Then I will talk briefly about quantum simulation, which was more broadly covered yesterday. And I turn to some other interesting models of safe preparation, which really don't fit the previous schemes, which are somehow dissipative and stochastic safe preparation techniques. And I will end with quantum walks and Grover search. I will see how far I go with this last topic. It's very tightly related to the singular value transformation framework, so we might just delay some parts of it for the next talk. So the quantum Fourier transform, it's one of the most powerful techniques in quantum algorithms, and this all started with the Dai-Jozsa algorithm. But before delving into details, this is the quantum Fourier transform, which is really just the discrete Fourier transform over n, and this is the matrix which for every column you have powers of an nth root of a unity, and this is the quantum Fourier transform matrix. In particular, if you just take a basis state J, then it gets mapped to a uniform superposition over all k's, but with different phases, and the phase factor is like this primitive root of unity to the j times kth power. This is another way of thinking about the quantum Fourier transform. And the simplest example of the quantum Fourier transform is just the Hadamard matrix, where it's a 2x2 matrix where every entry is a 1 divided by square root 2, except the bottom right corner is minus 1 over square root 2. And the nice fact is that QFT on power of 2 to the n can be implemented using only n times log n quantum gates, which is very quick. And the proof of this is actually the same as the construction in the fast Fourier transform, which has complexity n log n, which is exponentially worse, because in this case we need to write down the vectors explicitly, whereas a quantum computer can just work with the quantum states natively. So this is a very powerful tool, and this all started with the Dai-Jozsa algorithm in '92, which solves a first seemingly slightly trivial problem where we are given a Boolean function which is 0, 1 to the n, maps to 0, 1, and we need to decide whether this function is constant or balanced. And this algorithm just decides it with one query exactly, and the quantum algorithm needs some access to this function in a form, And this we model with an oracle, a binary oracle, which an input X and output register B just flips or not flips, flips or doesn't flip the second register according to the function value. So this is how we access this function. And the difference between the quantum model and the classical model, that in the quantum model we can ask queries in superposition. So this X can be really a superposition of different inputs. And the circuit which solves this problem is the following circuit. It's very simple. In fact, it's so simple that that people didn't appreciate this result very much at the beginning. Now it's really now we view it as a foundational result which started a lot of other algorithms, which I will show you are all generalizations of this same very simple circuit. But it's not so easy to be a pioneer in the field. When this paper was first finished and the authors wanted to submit to PRL, they got rejected. And the reviewers told them that, well, this is not a very interesting problem, and it's not good enough for PRL, so maybe they should instead solve the traveling salesman problem and then come back with a new result. Of course, we know that the traveling salesman problem is NP-complete, so no one really expects, or NP-hard, so no one really expects it to be solved by a quantum computer, but back in the days, PRL had very high standards. So let's take a look at this algorithm. How does it work? Well, really, this register is just here to put this register to a minus state, which is a uniform superposition of 0 and 1 with opposite signs. And this turns this function to a very funny kind of oracle. It's a phase oracle, because if we have a superposition of 0 and 1 with a minus sign here, then flipping a bit basically just flips the sign, just changes the phase of the quantum state. And this is called phase kickback. And therefore, what we see here, this Hadamard matrices create a uniform superposition over all possible inputs, and then changes the sign of the inputs where the function had a 1 value. And then if you again apply the Hadamard transform, it turns out that if the function is constant, then it doesn't change the phase or changes the phase over everywhere with a minus sign. So then the output will be just 0. And one can see that if exactly half of the inputs is 1 and half 0, so it's a balanced function, then we get something other than 0. Maybe it has at least one entry if we measure it. So what can we learn about this quantum algorithm? Well, this is one of the first demonstrations of how constructed interference can be used as a computational resource. And it also tells us that studying problems in the black box setting gives useful insight, and we can concentrate on what is really important. And the surprising fact that this quantum algorithm, which doesn't give much advantage, for example, if we had a randomized algorithm, you can just randomly query a few entries, and if you see both zeros and 1, it's balanced. If you don't see them with high probability, it's a constant function. So it doesn't really give much improvement over randomized algorithms. But we will see that the same circuit just applied to different problems will give really large improvements. So now we turn to the Bernstein-Vazirani algorithm, and the circuit is the same. I don't need to change anything, and this is a recurring theme in quantum algorithms. You need to figure out one algorithm once. It's very difficult. There are only like, I don't know, 7 examples that I showed you, maybe. And then you need to figure out what this algorithm actually does. And don't touch the circuit. If the circuit works, it's great. Just change the problem. And this is what we see here. We are given a Boolean function. Now it has some other property. We know that it's a linear function, mod 2. And the task is here to figure out what is this S, this linear factor in this function. And turns out that the same algorithm works. Again, we convert to phase queries, and it's very simple to work out the math. If you just run this algorithm with certainty, you will get S out in the measurement. And so this really shows the power of Fourier transform. Now here you should think about this Hadamard as the Fourier transform over Z2 to the n. And yeah, phase kickback has a surprising and useful quantum effect. And here the interesting thing is that if you think about this circuit classically, you really have only one output register. So you query a function, you get one output bit classically, and well, with information theory, you can argue that if you only get one bit of information, maybe if it's a quantum bit, you get like 2 classical bits in some cases, but no more than that. Olavo showed this. So how can it be that I only get like one output bit and I can learn n bits of information? Well, the trick is that this input register, which seemingly is not touched, is actually also used as sort of an output register by the quantum algorithm using the phase kickback. So really, here we get back not a single qubit, but n plus 1 qubits, and there is no contradiction that we can learn n bits of information using such a query. Now, this is a very surprising quantum effect. All right. So now I want to push forward to recent developments from these very early algorithms, catch up to 2018. And well, in the middle, there is Jordan's algorithm, which is just a generalization of Bernstein-Vazirani. And first I go through a less well-known generalization, where you replace the group z2 to the n by zk to the n. So now we have the promise that we have a linear function over zk to the n, and it has a similar form. Now it's mod k. And I don't want to worry about phase kickback bits. It's a bit cumbersome in this case to work with that, so I just assume right away that I have a phase oracle which computes this function in the phase for convenience. So then it turns out that the same algorithm works. We don't have now the ancilla because we don't need to worry about the phase kickback trick. But what we do, we just start with a 0 state. We apply quantum Fourier transform, which really just creates a uniform superposition, so it's like analog of Hadamard. And then we apply the phase oracle, and then we apply an inverse Fourier transform. And again, with certainty, you will get out S, this linear factor here. And this can be now generalized. Oh yes, here I wanted to say that, remember that the quantum Fourier transform mod k maps J to superposition where here in the exponent you have J times L. And you see the same thing here, except that we don't have the summation, so that's why we create uniform superposition, we add the phases, and we see exactly the state of this form, and when we apply the inverse of the quantum Fourier transform, we will just get back the linear cofactors, and coordinate-wise it works. So that's like a very quick intuitive explanation why this algorithm finds this linear vector always. And so if you go one step forward and you replace zk for a large k with the reals, it's basically like a fine-grained approximation of the reals. Think about it as a fine mesh. And if you have a real function, then you just define a fine mesh by some integer and do the same algorithm. So what does Jordan's algorithm solve? Now, suppose that we have a linear function, or like a function which can be well approximated by a linear function, for example, differentiable. Then around x0, say, the function looks like as fx0 plus the gradient times the difference from the origin x0. So we have a differentiable function which locally looks like a linear function almost. So we apply the previous trick, we discretize R and turn for a large enough k, and this k will really tell us the resolution, like how precisely we can compute with these real numbers. And then we just apply this function again in the phase, and we observe that when we compute the function in the exponent, then it really, because of linearity, it can approximately be written as a global phase factor. We don't care about this. And here we have this linear phase factor, which is exactly the thing that we need in this previous algorithm, in this generalization of Bernstein-Vazirani. And so if you just run the same algorithm, then with high probability, you will get the gradient out here as a measurement up to like 1 over k precision. But if the function is not exactly linear, then you might get errors, and in order to control how well this algorithm works, you need to be sufficiently close to a linear function.
Is the gradient constant in this function, or not really, right?
Yeah, okay, so this should be like grad f x0. This is the gradient at x0.
Sorry. wouldn't the wraparound will break the linearity property?
Yes, so when you take a finite mesh, you just take a small cube around x0, and then at that region, it's roughly linear. And
The QFT is going to act on the whole space.
yeah, so how you can think about it is that if you take the function once at a small region and it's linear and there is no wraparound, but maybe you will like apply the same phases together, the phases add up, and the phases will wrap around. So when you do this phase query, well, I didn't tell you that, I didn't constrain you from this phase to wrap around. This phase can be larger than 1, so I allow it to wrap around. Yeah, but if I stay close enough to the x0 point, then it's a linear wraparound. Yeah, wrapping around is important in quantum Fourier transform, and it happens, but it all works out. Okay. So, and now jump to some newer applications of this idea. So the key thing here is that if we can sufficiently precisely compute the function, then with only a single function evaluation, you can compute the gradient. And this is very useful, for example, in convex optimization. So let's take a look at convex functions. Convex functions need not necessarily have a gradient at every point, but at least they have one subgradient at every point. It's a hyperplane which touches or is at least below the function curve at the point. And if one works a bit harder, it turns out that because of this convexity property, you have the following extra result, that actually around most points, a convex function can be well approximated by a linear function. And then somehow, if you want the better approximations, then you need to look closer, like in differentiable functions, but somehow, despite the fact that you don't have differentiability, you still have this property that if you look close enough, then with very, very high probability, you are very close to linear function. And then the same story applies. And so how can you apply this result? I'm not sure it's very well visible. If you can't see it here, then the monitor shows better this picture. So in convex optimization, one of the important subroutines is that we want to optimize over a convex body, and then we have a point, a red point, which is outside this purple body. Then in order to find like a point or like optimize over this body, it's useful to find a separating hyperplane, which tells us that, okay, now you are outside of this convex body, and you want to find somehow in which direction is this body, where should you move forward in your optimization step. And for that, it's really useful to find a hyperplane which clearly tells that, okay, you are at the wrong side of this separating hyperplane, so go this direction. Yes?
How does the complexity of the QFT depend on this K?
You will choose K as a power of 2 in practice, and it's logarithmic. So it's log K. If you want precision epsilon, then it's like log 1 over epsilon. That part is right. Yes. So now suppose that you have a point outside this convex body, then and you suppose that you also know a point inside the convex body, then you can, from this point, look at the direction of the inner point, and the boundary of the convex body is just a convex function. And by only like checking whether a point is inside or not this body, like with binary search, you can very precisely find the boundary of this convex body. If you can ask questions, hey, is this point in the convex set or not? So now this is called a membership query. You can only ask whether a point is inside the set or not, and it gives you an evaluation of this boundary function, which is a convex function. Now you can apply the gradient computation. And it turns out that with a very few queries to membership, you can find a separating hyperplane with only like logarithmically many. And this is really an exponential speed up. Classically, you need, in the general case, at least n, which is the dimension of the convex body, and many queries to find a separating hyperplane. And unfortunately, this subroutine is not enough to like solve everything, all the optimization problems, but it's a very important step in many algorithms. So it gives like typically quadratic speedups for these convex optimization problems. And in general, you can't get exponential speedup for the full optimization chain, but at least it speeds up one of these steps tremendously. And this is a result which was shown by some of my colleagues outside in CWI, and at the same time Chakravarti, Childs, Lee, and Wu from Maryland. So it's really, it was a timely result. We independently found out this. All right, so now I showed you how you start from Daijo's algorithm, you generalize it to Brenston-Vazirani, and you just look at it differently, and suddenly you can find separating hyperplanes. Now, let's take another generalization of the Daijo's algorithm. Oh, but before, yeah, sorry, I forgot to mention this. This is just a comment to, like, this is just a connection to yesterday's talk. So actually, using this Jordan algorithm and the improved version of it, you can also get a quadratic speedup for computing the gradient of variational quantum circuits. So you get this 1 over epsilon scaling, which is not the log 1 over epsilon scaling we wanted, but at least not epsilon squared. This is just another application of the same ideas. So now let's move to another generalization of the Daijo's algorithm. And here we replace this Fourier transform not coordinate-wise, but we replace the entire z2 to the n by z2 to the n. So now we look at this Fourier transform over a cyclic group instead of z2 powers. And this gives a phase estimation algorithm, which is given a unitary. It has some eigen decomposition, some psi lambda eigenstates with an eigenvalue 2 to the pi I lambda. So we have this unitary, and we don't know this decomposition, but maybe we are given an eigenstate, and our goal is to figure out what's the phase, what's this eigenvalue in this unitary. And the circuit is again generalization of the Daijo circuit. We start with a Hadamard, and we put here this eigenvector. So this is the ancilla for the phase kickback. And the circuit, what we do, will apply powers of the unitary. And if you just do this simple circuit, it turns out that if you interpret this ancillary register as an integer number k, then for ancilla state k, it will apply the kth power of the unitary. So this is what this circuit does. And then if you apply it to the state, then it will apply the k times this phase. And so Fourier transforming this state in the register, in the ancillary register, will give you an approximation of the phase. So you start with an eigenstate, you apply Hadamard, so you get a uniform superposition over the ancilla states. You apply the circuit to get the appropriate phase with lambda times k in the exponent, and as if lambda is like a multiple of 1 over 2 to the n, then the inverse Fourier transform will exactly write down lambda in binary in this register. And if lambda is not exactly a multiple of 1 over 2 to the n, then still with high probability you will get a number which is close to this binary representation. So this is a little bit of annoying technicality that you don't exactly get what you want, but with high probability some rounding, but in most applications it doesn't really matter, it's good enough for you. So this is phase estimation, and phase estimation, as Ike mentioned yesterday, is the essential element in Shor's algorithm, but Shor's algorithm fits an even more general framework in an algebraic setting, which is the hidden subgroup problem. And here now we do one more step. In Shor we had Z2 to the n as our group, and here just replace your group with an arbitrary group, or well, in the efficient version with an abelian group. And so the following is the problem. We have oracle access to a function which acts on group elements and maps to some finite set. And the promise is that we have a subgroup H such that the function is constant on the cosets, but differs on every coset. So x and y has the same value if and only if x and y in the same cosets. And the goal here is to find this hidden subgroup H, maybe in terms of writing down a set of generators. And the algorithm for solving this problem is given by Kitaev in '95. And here it's just you start with a uniform superposition over your group elements. This corresponds to the initial Hadamard in the Dajjoz algorithm. You apply your function and then Fourier transform, measure, and it turns out that this simple algorithm, which is really just replacing the Fourier transform with a different one, again solve this problem and works nicely for abelian groups. And it turns out that it samples a uniform random character or irreducible representation of the group, and one can then find a generator system of H after a few repetitions. And Kitaev showed how to implement this Fourier transform efficiently, so we can really work this out efficiently. And here is Simon's problem, where the hidden subgroup is just in Z2 to the n, and you have period finding, which is Shor's algorithm, and the discrete logarithm problem can also be cast as this problem. Okay, so it really has many, many applications, and these results were later generalized. For example, one can show how to solve Pell's equation, which is this equation, and solve the principal idea problem. It's in the same paper by Hallgren, 2002. And then you can extend period finding to the reals and some vector space over the reals. You can compute the unit group of number elements and break elliptic curve-based cryptography and many things more, which I don't have time to talk here about, but Sean Hallgren will talk about related algorithms on Thursday. And so the non-abelian hidden subgroup problem, people try to use the same algorithm, but doesn't go through it explicitly. It's harder to define the Fourier transform, and sometimes you can implement efficiently, sometimes not. But the main problem is that it's unclear how to recover this subgroup efficiently. And it turns out that the same algorithm works in a query setting that running this algorithm a few times will provide you enough information to somehow recover, in a quantum sense, this subgroup, but it's not efficient. So we don't know how to do it efficiently in general. And there was a long sequence of works on this problem, and people could solve some subcases, but it has become increasingly hard, and the progress slowed down kind of exponentially because it's a really difficult topic. But there is one very interesting example of Kuiper-Bers algorithm, which solves the hidden subgroup problem in the diahedral group, and it has sub-exponential runtime, which is one of the basic tools to attack lattice-based cryptography, or someone is here from the other workshop. And here is a cute example of a problem which can be solved using this hidden subgroup problem if we can solve this in a non-abelian case. So it's a graph isomorphism, and here the group that we take is a permutation group over 2n, and the function is that we permute the vertices of the graph G union G prime. So we take the two graphs G and G prime, which has both n vertices. We want to figure out if they are isomorphic or not. We just take all permutations, and so what is the hidden subgroup which is hidden by these permutations? Well, it's the automorphism groups of G union G prime. Just leaves this permutation intact, so it doesn't do anything, and all the other permutations do something else. So the goal here is to find out which is the automorphism group of G union G prime. And if we can write down a set of generators, we can see whether there is a generator which interchanges any vertices in G and G prime. If it is so, then it means that G and G prime map to each other because they are disjoint. And well, here we assume that G and G prime are connected without loss of generality. So if we can interchange them by an automorphism, it means that G and G prime are isomorphic. So G and G prime are isomorphic if and only if the automorphism group contains some permutation which interchanges the two graphs. So really it's an important problem, but we don't know how to solve it in general. So here I show you an alternative approach to solve graph isomorphism, which is based on the swap test. So imagine that we can prepare a uniform superposition over permutations of graph G. We can also prepare a uniform superposition over permutations of G prime. Now observe that these two quantum states are the same if G and G prime are isomorphic, because it doesn't matter which permutation I started with. But if the two graphs are non-isomorphic, then all kinds of permutations of two graphs are always different. So then the inner product will be 0. So if we can figure out the inner product between two quantum states, which are either 1 or 0, then we can solve graph isomorphism, while modulo the technicality that we need to prepare this uniform superposition, which turns out to be the challenging part. And the swap test is very simple. You just prepare the two states and use an ancilla in a plus state, which is a superposition of 0 and 1. And based on the value of this state, you swap the two registers and then measure the ancilla in the plus-minus basis. And the probability of getting outcome plus is 1/2 plus half times the inner product squared of these two vectors. So really, if we can prepare these uniform superpositions, then doing the swap test a few times tells us whether the graphs are isomorphic or not. And this idea is actually also used in an attempt of trying to break lattice-based algorithms and cryptography. There, you want to prepare uniform superposition not over permutations of graph, but you want to prepare uniform superposition of lattice points with some Gaussian noise around it. So suppose you can prepare this uniform superposition, and now take your vector, which you want to figure out, is this vector close to the lattice or not? What you do, you shift your uniform superposition by this vector, and if this vector is like 0 or very close to 0, then it barely changes the state, slightly shifts the sides, but the two Gaussian distributions around the lattice will have high overlap. So you start with this Gaussian around the point, you shift a little bit, and it will still have high overlap. If the vector was short, like compared to the width of the Gaussian distribution, then the overlap will be high. But if the vector was long, then you shift these Gaussians around the point far apart, and they no longer overlap. Then the overlap between the two states, the inner product, will be small, and you can conclude that the distance of this unknown vector, which I shifted my state with, should be further than this width of this Gaussian distribution. So if you can prepare such a uniform superposition, you can basically solve a decision version of the closest vector problem, and it has bad implications to lattice algorithms, but unfortunately we don't know how to prepare this, or well, maybe fortunately, it's depending on your point of view. We don't know how to prepare such superpositions, so this attack doesn't work in practice. Okay, so here I want to just gloss over another application, which is viewing unitaries as representations. So yeah, this algorithm is based on the Hadamard test, which is another test which is used for estimating the expectation value, or at least the real part, the expectation value of some quantum state. You can also figure out the imaginary part by modification of the circuit. So based on this idea, if we have a quantum circuit, we can somehow probe matrix elements of it. And this will be very useful in this application when this quantum circuit U comes from some representations of an interesting group. So if we have unitary representation of some algebra, then unitary just corresponds to a quantum circuit, and we can probe some matrix elements using the Hadamard test, which is very useful in the Jones polynomial, in the problem of Jones polynomial. So what's the Jones polynomial? It's a link invariant, which a link is just a collection of some closed curves in 3 dimensions, which may be intertwined with itself or with other loops. And a link invariant is a way which is a quantity which helps us to find out whether 2 links are isomorphic, they can be continuously transformed to each other or not. And so the link invariant is a quantity which doesn't change under these smooth transformations, and the Jones polynomial is such an invariant. And so it maybe helps us to distinguish between this. Who can see what's this curve? When I draw it down, I didn't intend to draw this, but figured out that
It's a circle.
it's just, yeah, it's 2 circles, so it's just like this. I wanted to make something more complicated, so I actually wanted to draw this because it's no longer a circle, and Jones polynomial could help you distinguish these 2 cases, for example. I'm not sure if this exact distance is distinguished though, because it doesn't distinguish everything, unfortunately. So from links, here we move to braids. Braid is a collection of parallel strands where adjacent strands are allowed to cross. And one can form a link from such a braid by just connecting the bottom and the top parts of these strands. And one has some freedom how to connect these top and bottom parts. And based on that, we can define different closures. And the nice thing about braids is that they form a group under the operation of concatenation. We can just put these figures on top of each other and we get a new braid. And so we can study the Jones polynomial of various links formed by these braids. And here we can use the algebraic structure of braids. And there is the Temperley-Leib algebra, which is a representation of the braid group. And if we substitute a root of unity to this Jones polynomial, then the relevant representations of this algebra are unitary and corresponds, and so the approximate value of the Jones polynomial can be evaluated by just a matrix element of unitary, and this unitary is really just a quantum circuit which comes from representations of this algebra. It turns out that this is a BQP complete algorithm to compute the Jones polynomial due to Aharonov, Jones, and Landau. And there are interesting connections to topological quantum field theory as shown by Witten. And so there's very deep connections. Friedman, Kitaev, Larsen, and Wang showed that quantum computers can efficiently simulate topological quantum field theories, but this result about the Jones polynomial gives an alternative proof of that result. So now here we start to arrive at simulation and connections to between circuits and simulating some field theory or some physical theories. And this brings to another big application area, which is quantum simulation. And I talked about this yesterday. It is just the problem here is that we have the Schrödinger's equation, and for simplicity, assume now we have a time-independent quantum system. The Schrödinger equation just says that the evolution of a time, the derivative, is proportional to the Hamiltonian of the system, and the closed form solution is just I need to exponentiate the Hamiltonian and apply this to the initial state. And a matrix function, which is this exponentiation of h, it's defined as the following way. It will be useful because we will, in the next talk, we will talk about different kind of matrix functions, so it's useful to see the difference. So we have a Hermitian matrix H here. We can diagonalize it in an eigenbasis. It will have real eigenvalues and some corresponding eigenvectors. It's a symmetric diagonalization. And then if we have any function from the reals to the complexes, then we can just apply this function to the eigenvalues, and this is how we get the matrix function. This is how we define it. And here, when I talk to physicists, I often get the question that it doesn't make sense. We want to build a quantum computer, which is basically by simulating Hamiltonians, And once we built a quantum computer, we want to simulate Hamiltonians. So it seems like a circular argument. But it's not like that, because in a quantum computer, we build a few set of quantum gates, and we only need to ensure that those work very well. And then the simulation results that I showed yesterday ensure that we can simulate much broader class of Hamiltonians once we have this very small gate set. And yeah, so this I will not talk much about because I will cover. This is the first idea, which is trotterization to simulate Hamiltonians, which is just breaking up the time evolution to small time steps and repeat those. But there was later a long sequence of works which were covered yesterday, and really the optimal Hamiltonian simulation in the query model was by the quantum signal processing technique of Wang Hao and Ike, and this achieved an optimal scaling. And well, this looks much better than the trotterized algorithm. In practice, it turns out that the trotterization is still a very competitive method because it can somehow better capture some advantage coming from the physics of the system. So there was a very nice recent survey which is already slightly outdated because of the fast pace, but it motivated a lot of research by observing that our theory needs to catch up with what actually happens in the lab. And there was a long sequence of papers just in the past 2 years. It was amazing how much new development happened there. We have new methods for time-dependent sparse Hamiltonian simulation from last year, which shows some very nice scaling, which is somehow the cost of the simulation is the sparsity times the average maximum matrix element. And this is like a very nice optimized result. On the front of quantum chemistry, we have also improved algorithms which uses some clever choice of bases, some plane wave orbitals, and so that's n, and we have some 8 number of electrons, and achieves this nice complexity, which is again 10 years ago these numbers looked much worse. Now it starts to seem like something practical, at least in a fault tolerance regime. And then we have algorithms for lattice Hamiltonians, which can very well use the locality of the structure and somehow only pick up a linear dependence on the number of sites and time t. And there were many other interesting ideas. Recently, some of them presented at QIP 2 weeks ago. And there is much more to explore here. Now we simulated some chemistry, some more discrete systems, but in general, we have quantum field theory, which describes the quantum mechanics of fields around us. And there are still a lot of questions unsolved there, and we still need to find better ways to simulate. Quantum field theory is what we see in nature. Nature has quantum field theory, and so we ought to be able to simulate quantum field theory if nature can. So this is a very interesting research direction, and John Kresge has a very nice recent survey about it. Okay, I want to briefly now turn to a different set of quantum algorithms, which is based on the dissipative and stochastic processes to approach state preparation. And the interesting thing about this approach is that it's completely different from the previous algorithms. It has nothing to do with those, or maybe has some slight connections, but it's a very, very different idea on its own. It doesn't have so many applications so far, but I like this because it's a completely new approach, and it turns a resource, like an adversary to a resource. Like dissipation is something that we don't want. We want to avoid, we want to protect our quantum system in general, but it turns out that if you drive dissipation in a clever way, you can actually turn it to your advantage. And so this is used mostly for preparing ground states of frustration-free Hamiltonians. And so what's a frustration-free Hamiltonian? It's a Hamiltonian where you have local terms, but you have the property that there is a quantum state, which is in the ground state of every local term simultaneously. So if you are from a classical perspective, if you have a satisfiability problem, like a K-set problem, it means that you have a satisfying assignment. Because in set, like each clause is like a penalty, and you can say that if a clause is not satisfied, it gives you penalty 1, and therefore a ground state here would just be a classical bit string which avoids all penalty terms, meaning that it satisfies the entire formula. And Hamiltonians generalize it into a non-commutative setting in the quantum world. And so if you are coming from a classical background, please read this algorithm that I will show you in a classical language. Ignore all quantum and think about satisfiability problems. And if you want to view the quantum version, just replace everything by quantum and the same thing works. So this is the famous resampling algorithm. And here we try to find a satisfying assignment or a ground state if you wish. And the algorithm is super simple. It says that while not all constraints are checked, then we need to do some work. Let's pick an unchecked constraint and check it, or in the quantum case maybe measure it. And if this constraint is not satisfied, then randomly resample all the adjacent bits, so all like bool variables or qubits which are in this term. And once we did so, we might need to recheck all the adjacent constraints because some qubits relevant to those changed. So we need to mark all adjacent constraints unchecked. And just do it in a loop until you checked everything. And so this is a very simple algorithm, but and it works also for quantum states, and one can show that this algorithm always finds a frustration-free ground state. And this was proposed in the quantum setting by Verstraete, Wolf, and Sirac in 2008. And just in the same year, Moser came up with an algorithm which is the same algorithm, but in classical setting. But Moser was able to show that it's an efficient algorithm in some sense. So this is the efficient version of the Lovász local lemma by Moser and Tardos. And Lovász local lemma tells you that if you have a constraint system where somehow you don't have too many constraints and the constraints are not too much overlapping, then you always guaranteed to have a satisfying assignment, but in a non-trivial way. So this goes way beyond like union-bound arguments and independence arguments. This is somehow in the middle, and it gives you non-trivial results. And under this Lovász local lemma condition, Moser and Tardos showed that this very simple resample algorithm finds a satisfying assignment quickly, efficiently in polynomial time. And then people in the quantum side catched up. They matched this quantum idea with the classical result. It showed that if in the Hamiltonian all terms are commuting, then the same algorithm is still efficient and still works nicely. And this was independently proven by Satat and Arad and Schwartz, Qubit, Verstraete in 2013. But the proof somehow broke down in non-trivial ways for non-commuting Hamiltonians, and we were able to fix it for a family of Hamiltonians which were non-commuting, but they had some gap assumption that somehow non-commuting terms didn't combine too badly, and there was a gap which had distinguishing those, and we had this result in 2016 with Orsatat. And this algorithm, deep inside, will again use. This was actually my first connection to quantum single-body transformation, because somehow the quantum step which needs to be changed in this algorithm is somehow deeply related to that, which I only realized 4 years after. So it really was a long journey for me as well. And here I just want to mention a loose related result just for completeness of in this scope of quantum algorithms. There is a quantum metropolis sampling algorithm, which is a stochastic state preparation, and this is a heuristic algorithm, but people hope that it will have similar success as the classical Monte Carlo algorithm, the Metropolis algorithm has. Okay, and now I want to turn to the quantum walk setting, at least start this before the next talk. And this is another very successful paradigm of quantum algorithms. Before I go and define the continuous quantum walks, I wanted to define what is a quantum walk on a graph. So we have a graph on the vertices V and edges E, and we have non-negative edge weights. And the Laplacian of the matrix is defined as LUV, the matrix element between U and V for different vertices is just the weight. And on the diagonal, we have minus times the sum of the weights of the matrix. So it's the sum of all the weights adjacent to vertex U. That's the LUU element. So in particular, any row or any column of this Laplacian sums to 0. And using this Laplacian, we can define a continuous time Markov chain, a walk, where the distribution, the probability distribution on the graph satisfies this differential equation. Somehow the change on the probability mass at vertex U is proportional to the weighted sum of the adjacent vertices. And this differential equation can be solved as we just need to exponentiate the Laplacian. And so this looks very much like Schrödinger equation that I showed you before. And indeed, we can just replace this equation by the Schrödinger equation, just put an I here, and then I say that the amplitudes change proportional to the amplitude of the neighbor vertices. And now the solution of this linear differential equation is just the Hamiltonian simulation of the Laplacian L, and this is defined as the quantum walk, a continuous quantum walk on the graph G. And I would like to end this first half of the talk by a very nice result, an application of this continuous time quantum walk framework by Scheitz, Cleve, Biotto, Farhi, Gutmann, and Spielmann. And so they studied the following problem. Suppose that I'm given a graph, which is a binary tree on this side, and a binary tree on the other side, but in the middle, every vertex is connected to two other vertices on the other side, but in a random fashion. So I don't know how is this connection looking. I only know that the graph has this structure overall. The only thing I'm given this point on the left. And so this is like the entrance point, and my goal is to find the exit point. And how can I recognize that something is the exit? Well, this graph has a nice property that every vertex has exactly 3 neighbors, except the entrance and the exit. So if I'm given the entrance, there is a unique other vertex which has only 2 neighbors. This is the exit, and my goal is to find this. And it turns out that if I run this continuous time quantum walk, then with a few number of steps, I will reach the exit. So I just run the quantum walk and measure, and after some number of time steps, a proportional polynomial in the like depth of this binary tree, I will find the exit. And this happens. It's another nice constructive interference pattern. What happens here? Somehow the quantum walk doesn't really distinguish these paths. It just spreads uniformly, and it doesn't matter how these things are connected. It just spreads through this middle part and arrives here. And it only does local steps in every step. So it's a local algorithm. And this is exponentially quicker than anything possible using a classical algorithm, because a classical algorithm, if you can only see the neighbors and you only can query neighbors, like the quantum algorithm did, then you just get lost. Once you get here, so initially you will probably quickly converge to the bottom of these leaves, but then you start getting lost in this huge three-regular graph. You maybe make a step forward, but then you step back and you don't know. You just lose track. You no longer know where you are. And it can be proven rigorously that there is no efficient algorithm which finds this other way in efficiently. So this is a really large quantum speedup. And in the next talk, I will talk about discrete time quantum walks, but this is the topic of unique singular transformation, so I will end up here and wait for questions.
Thanks for a nice talk. So I was wondering about the preparation of ground states of frustration-free Hamiltonian. Can you go back to that slide?
Mm-hmm.
Yeah, the algorithm. I was wondering if you could explain it a bit more in the quantum case, a bit more specifically what's going on. So you pick some random state to start out with?
Yes, you start a random state, which is like a maximally mixed state.
Okay.
But you know, actually just picking a random bit string is also a maximally mixed state. So you can just do that as well.
Okay. So you do that, you measure, and what about this random resampling? That's also, you're just picking them as maximally mixed?
Yeah. So you throw away those qubits and replace them with a maximally mixed state. But again, you can just think about this completely classically. Just throw away those qubits and just replace them by a uniform random bit string. So the same thing that works in a classical setting also works in the quantum. You just need to think a bit differently about it.
How fast is this?
Yeah, so it's usually something like linear in the number of constraints. Once you are below this like lowest threshold, and maybe you are not extremely close to it, then it's like linear in the number of constraints. Even if you are quite close to it, it's still usually like linear or like very small polynomial.
What does it mean below the Lobach threshold?
So I said this vaguely, this constraint. So if you have, so your constraints should not be like, you shouldn't have too many constraints and they should not be too overlapping, because if you have very overlapping constraint, then they can already rule out everything just on like a few bits. And so there is like a quantitative bound which is actually tight. It's called the Shearer bound is the tight version. And so if you like, maybe if you add two more constraints, then suddenly the bound is no longer satisfied, and you might be in a situation where there is no satisfying assignment, there is no ground state. So you should be below that at least there should be a solution that you are looking for. If there is no solution, you can't find it.
If you always pick random bit strings in this algorithm, how do you ever get a ground state that's a superposition of computational basis states?
Yes, good question. So in the classical setting, when you have like a k-sat formula, you will not. However, if you have a quantum Hamiltonian, then when you do this measurement, then this is this dissipative set that I told, then this will be a measurement in some non-diagonal basis. So it will somehow start to make your initial state, which was a basis state, it slowly transform it into something, and a long sequence of measurements can create a high amount of entanglement.
So partial measurements?
Yes, these are measurements. So these are local Hamiltonian terms, maybe acting on, say, three qubits, and you only measure those 3 qubits regarding that Hamiltonian or projector that you have.
So, would such a thing actually allow you to prove an area law? If this kind of approach works? So you're generating entanglement only at a certain rate. So would you be able to?
Maybe. The problem here is that this Loas or like Shearer bound is quite restrictive. So it doesn't say area law would be somehow going in the other direction. Like suppose that I have a gap then I have area law. And here it just says that suppose I have like not too many constraints and I have a gap. So it's a stronger constraint that we have on the form of the Hamiltonian. It's gapped plus sparse, let's say it that way. And in that special setting, I believe it would prove area law, but this is a much more restrictive setting than what physicists want to prove.
The question, if there's not another one. So back to Stephen Jordan's algorithm and your gradient algorithm, that implies another model of quantum computation as well, where one has continuous variables instead of discrete qubits. Are there other classes of algorithms that could show gaps in that different model?
How we handle this like continuous setting is that we always discretize everything. I didn't tell it because it's technical, but we always just like truncate the bits at some point and then work with finite bits, because like working with infinite dimensional Hilbert spaces is very dangerous, especially as shown by this recent result of MIT star plus RE. So everything that I showed, everything is truncated, and then there is no issue of this continuity.
In principle, you don't have to. You just have to be much more careful. And I'm wondering if there's a good reason to do any of that, to go and stay continuous.
It's a very interesting direction, but we didn't study how you do that.
Other questions? Okay, if not, let's give this